Section 4.7 is scientific notation. I can write numbers using scientific notation. A number is written in scientific notation if it has the form c times 10 to the nth power, where c is more than 1 but less than 10, greater than or equal to 1 and less than 10, and n is an integer. Basically, we need exactly one number in front of our decimal that's not 0. Could be 1, could be up to 9, but only one number in front of our decimal, and it can't be a 0. So standard form is where it's all multiplied out. All the zeros are there. We read it as 725,000 or 6 thousandths. In product form, it tells us our decimal times our power multiplied out. And in scientific notation, we take our decimal, exactly one number in front of our decimal place, times in exponent form 10 to the blank. Notice here, numbers that are bigger than 10 have positive exponents, and numbers that are smaller than 10 have negative exponents. In example 1, we're going to write numbers in scientific notation. The retina has 120 million rods. Write this number in scientific notation. So here, we only worry about the 1 and the 2. All the rest of these zeros, we don't care about. We only care about zeros if they're in between non-zero numbers. So if it was like 1, 0, 2, 0, 0, 0, 0, then we care about the 0. But otherwise, we don't. Not in scientific notation. So I write my 1 and my 2. We want exactly one number in front of our decimal. So I put my decimal after the 1. Now, I count how many places the decimal would have to move to get back to where we started. Here, it's 1, 2, 3, 4, 5, 6, 7, 8. So, we say times 10, and we use that 8 as our exponent. So, we get 1.2 times 10 to the 8th power rods. And because it's a big number, it's a positive 8. We'd have to multiply by whole tens to get there. The thickness of the human retina is 0.00012 meters. Write this number in scientific notation. So again, we just care about our numbers from where they start in relationship to our decimal. So these zeros we don't care about. We want exactly one number in front of our decimal, so it goes between my 1 and my 2. Then we count how many places we'd have to move to get back to where we were. Here, 1, 2, 3, 4. So, we multiply times 10 to the negative 4th. Because it's a small number, we move from where our decimal is to where it was. We moved towards the negative numbers on a number line. It's a negative 4th, and that is meters. So it's going to be 1.2 times 10 to the negative 4th meters. Tiny numbers get negative exponents in scientific notation because negative numbers are smaller than positive numbers. So bigger numbers than 1.2, for example, get positive exponents, and smaller numbers than 1.2, like numbers with 0 after the 0.00012, for example, get the negative. Negative numbers are smaller than positives, so that's one way you can remember. In example 2, we're going to work backwards. We're going to write numbers in standard form. So we're going to write 3.2 times 10 to the 7th in standard form. Write my numbers. Now, we need to move 7 places from where our decimal is now to where it needs to be. So, we go 1, 2, 3, 4, 5, 6, 7. And we fill those with zeros. 1, 2, 3, 4, 5, 6. It's not 7 zeros because I have that 2 there, so keep that in mind. It's 7 decimal places, but the 2 counts. So here, every 3 we put a comma, so we get 32 million. and it's 3 from the back, from our decimal. Here, we're going to write it in standard form. So, 8, 6, 9, I write down. I move my decimal towards negative numbers because it's negative here. So I go 1, 2, 3, 4, 5, and that's where my decimal goes. We fill with zeros. So I get 0.000869. Keep in mind, it's not 5 zeros, it's 5 places. We count the one with the 8 in it as well. And remember, negative numbers give us small numbers, positive give us bigger. So that's one way to remember which way to move your decimal. Feel free to pause here and give this a try if you'd like. We're going to write these numbers in scientific notation. So the 4 and the 1 are what I'm going to worry about. We want exactly one number in front of our decimal. Here I'd have to move it 3 places. 1, 2, 3 to get back to where it was. So I multiply times 10 to the third. And it's a positive 3 because it's a big number, and we moved it, we'd have to move it back to towards positive numbers on a number line, towards bigger numbers. So it's a positive 3. The only numbers I worry about here are the 6 and the 7. We want exactly one number in front of our decimal. Here, we have to move it to the left, which is going to give us a negative value, times 10 to the, it's going to be negative. We count 1, 2, 3, 4, 5 places. So, to the negative 5th. Again, small numbers get negative exponents, big numbers get positive. So 6.7 times 10 to the negative 5th power. Again, it's not just how many zeros, it's how many decimal places. So we include the 6, we include the 1. Try 3. We care about all the non-zero numbers unless zero's in between them. So if it was like 3046, then we'd care about that 0. But otherwise, we do not. We want exactly one number in front of our decimal, so we put our decimal after our 3. It's always times 10. Here we count how many places we'd have to move to get back to where our decimal was. 1, 2, 3, 4, 5, 6, 7. So it's times 10 to the 7th. And because this is a big number, it's a positive 7. So 3.46 times 10 to the 7th. Again, because it's bigger than 3.46, it's a positive. And in 4. We care about the 1, 4, and 5. We want exactly one number in front of our decimal. We're going to multiply it times 10 to an exponent. Here, to go from our decimal back to where it was, we move 1, 2, 3, 4, 5. And since that's in the negative direction, it's a negative 5. This number is smaller. The number we started with is smaller than 1.45, so our exponent has to be negative. So 1.45 times 10 to the negative 5th. Now feel free to pause here and give this a try. We're going to write the numbers in standard form, which is just working backwards. So here, I write my numbers. Since we want a positive 4 as our exponent, we move in the positive direction with our decimal. So I move 4 places, 1, 2, 3, 4, in the positive direction on a number line. Remember, since my exponent is positive, I should have a bigger number. And here, I get 71,000. 3 from the back gets our decimal. In 6, I have 193. We write our digits without the decimal. Now, we need to move it negative 3. So towards negative numbers, 1, 2, 3 places, and that's where we put our new decimal. We fill with zeros. So I get 0.00193. It should be a smaller number than 1.93 because my exponent is negative. Give 7 a try. Here, my numbers are 3, 6, 4, 1. My exponent's a negative 6, so I'm going to move it 6 places to the left, like negative numbers on a number line. 1, 2, 3, 4, 5, 6. That's where I put my decimal. We fill with zeros. So I get 0.0000361. Again, that does not tell us how many zeros. It tells us how many places we move. And give 8 a try. 5, 5, 9. We're moving 8 places. Since it's positive, we're moving in the positive direction. 1, 2, 3, 4, 5, 6, 7, 8. And that's where my new decimal goes. Again, we fill with zeros. From the back, every 3 is a decimal, or is a comma. And here I get 559 million. To compare numbers written in scientific notation, first compare the powers of 10, then compare the decimal parts. So we want to have these all in the same format. We're going to put them all in scientific notation. My first and my third are, but 3,800,000 is not. So I'm going to put it in scientific notation. We count one number after our decimal, or before our decimal. We count 1, 2, 3, 4, 5, 6. So times 10 to the 6th. So we're comparing these. We want from least to greatest. So we're going to compare our exponents first on our powers of 10. 10 to the 5th is smaller than 10 to the 6th, which means that 4.2 times 10 to the 5th is going to be smaller than the other two because it's being multiplied by 10 one less time, so it's 10 times smaller. Now, we need to compare our last two numbers. Here I have 3.9 times 10 to the 6th and 3.8 times 10 to the 6th. They're both multiplied by 10 to the 6th, so then we compare our decimals, 3.9 and 3.8. And 3.8 is smaller than 3.9, so that's our next least, and our greatest then is the 3.9 times 10 to the 6th because 3.8 is less than 3.9. And there we go. And I'll continue here in another video.